John DeGose. I am presently CTO of a company called Precog. And what we do is essentially produce a big data analytics engine. And thus I/O is extremely important to me. Personally, I am a committer and also the original author for a web framework for developing RESTful APIs in Scala called Blue Eyes. And obviously a web framework is predominantly concerned with I/O. And here at Precog, where we live and breathe I/O all the time, 100% of every day, for the purposes of doing analytics on large amounts of multi-structured data, you can imagine how important a topic this is to me. I've been using Scala for probably about two and a half years professionally, and I've kind of fallen in love with the functional way of doing things, studied a bit of Haskell, and really interested in kind of the intersection between functional programming and performant I/O. This is my laundry list of requirements for an ideal functional I/O system. You can see it's not small. Number one, I want any functional I/O system to be resource safe. So it should be very difficult or perhaps even impossible for a developer to do something like accidentally close a resource. I don't want resources leaking left and right. It should be composable. I should be able to take things that consume some input and consume them together, or compose them together in various different ways. I should be able to take things that produce output and also compose them together in different ways, because that gives me the ability to reuse code. It should be pure, or at least as pure as possible, because I want the benefits of reasoning and modularity and testability that come with pure code. And by pure, I don't mean even the I/O monad. I mean, we want to push even I/O out as far as possible and make our code pure in intention and not just in, yeah.
Pure as in the external interface or pure as in the implementation?
As pure as possible, but pure especially in the external interface, not necessarily the implementation. I also want the code to run really, really fast. And part of that is because my two projects are either the big data analytics database or this web framework, and either of them are subject to very, very strict performance requirements. I also want as much type safety as possible. I want the compiler to catch as many problems up front at compile time as possible. Like ideally, I shouldn't be allowed to, if close is an operation, I shouldn't be allowed to close something more than once, for example. Number 6, I want it to be as simple as possible. Obviously, the more requirements you add, the more incompatible with each other they become. And in particular, some of these on the JVM and in the Scala programming languages are unachievable together. But to the degree that it's possible, I want something to be relatively simple, something that doesn't take a lot of brain power to understand. I want it to be capable of incremental input and output, especially when you're dealing with modern web applications which frequently have to process hundreds of connections, maybe thousands of connections a second, or the kind of I/O that we do at Precog. You can't hold all that stuff in memory, and you need to be able to do operations incrementally on that. And finally, I want the I/O system to be very expressive. And I'll give you an example of what I mean by that. Frequently, when you're writing a web application, you'll be consuming input from the user, and then you'll dynamically make a decision to, for example, look at something in the database. And then based on that result, you may decide to read something from a file or open a new web connection. And basically, you need the ability to dynamically decide to allocate new resources at virtually arbitrary points in your code. And that requirement in particular is a real pain to get around in a functional system. So I want to kind of give you an example of classic I/O probably most people in this room have seen at one point or another, and it's based on Java's input stream and output stream. How many people have used this at one point in their career? Nearly everyone in the room is familiar with this. It's kind of straightforward, and I want to put it through a report card. How does it stack up to my laundry list of requirements? Resource safe, not at all. So you'll frequently see it in code that uses input and output stream, try catch littered everywhere, and that's because if you accidentally forget something, if you forget that finally block on any of your code and forget to free the resource, then suddenly you have a resource leak. And there's almost no Java application out there that hasn't had or been beleaguered by resource leak problems. Composable, it doesn't actually get an F, and the reason for that is because you can take an input stream and another input stream, for example. You can compose them together in a variety of different ways to get another input stream. And you can also take an input stream and you can decorate it with another input stream to add some bit of functionality. So they're a little tiny bit composable, which is why they don't get an F in that category. Obviously, they're not pure at all. It's straight mutation. There's nothing pure about that interface whatsoever. They get an A in performance because input and output streams are really, really fast. Not an A+, mind you, because they're based on synchronous blocking I/O, but they do get an A for performance. Most of the really fast open source projects out there written in Java that do I/O use input and output streams. Number 6, they are simple. So any developer can understand what these things do. So they get high marks for that. They do allow incremental I/O. That's a very natural way to use them. And they're expressive in the sense that obviously all this, tangled mess of imperative code can open up new resources at any point in time in response to anything. And so yeah, they're expressive within the paradigm that is input stream and output stream. Let's take a look at another means by which we might do I/O. And there's a lot of different concepts here. This family of concepts is referred to as iteratees. And iteratees were invented long ago in the Haskell community, and now they've since shown up in the Scala community. I want to derive the development of an iteratee step by step. And lest you think that this is purely theoretical, iteratees actually form the basis for several Haskell web frameworks, which operate very, very, very fast. And they also form the basis for, at Precog, our analytics database. And I think we're the first company or organization in the world that can claim to have an analytics database implemented on top of iteratees. So what's the basic idea here? Well, everyone's familiar with fold, right? How many people know what fold left is and have used it a billion times? So the basic idea is if in this fold function, you pass a list and you pass the function, which then computes new state as it goes along, and it ends up producing some final value. This looks like a lot of I/O problems. Many times you'll be reading through a resource and doing something, passing state along, and then you'll end up computing some sort of final value. And the really nice thing about fold is that if you translate it to an I/O context, then basically the list, or whatever is doing the fold over all those elements, has explicit control of the resources, which means that this abstraction provides a very convenient way to guarantee no resource leaks. Also, just by its very nature, you can see this F function is incrementally processing every element one at a time through the list, so it's giving us some of the benefits from my other chart. We get that incremental processing, we get resource safety, and you'll see these things evolve naturally as we make a few tweaks. So in this particular example, this is a nice starting point. But one of the problems is that we might like to consume a little bit from this list and turn that into one value, and then consume a little bit more and turn it into another value. So this property can be referred to as horizontal composition of these F functions, which I'm soon going to call an iteratee. And this gives us the ability to do really interesting things, like we might have a byte array and we want to convert that to a list of strings, a list of lines. Then we might want to consume the HTTP header portion and then consume the body. One iteratee to consume those bytes and produce a header, another to consume the body bytes and produce a body. And this horizontal composition property allows us to do that. How do we do that in code? Just very simple modification to what we had before. It's still called fold left. It's still folding over a list. Our F function takes the initial state, the seed, and an input element, and returns something called a step. And the sole purpose of step is to give the folding function enough information to decide when F no longer wants input, when F is done. So here you can see I have two different cases here. F function can return either a step that says it needs more input, or a step that says, I'm done, I don't need anything else. Notice the values being stuffed into these more and done data structures are actually the state of the fold function. Just like your ordinary fold function maintains state as it's going along, ultimately culminating in the final value. So also this value here is that state function that's passed along. And this turns out to be a rather inconvenient way to model state because you're being very explicit about it. You have to have a data structure that unifies all the different state decisions you make over the course of that fold. So one thing we can do to improve this definition is to move that state, which is currently contained in that parameter b, inside the function. And of course, a function can't have any state. So what we do is end up introducing a Mealy machine, which is a function that accepts some input and returns the output along with the next successor version of the function. And that function basically has a memory. It can remember stuff that has happened before and thus allows you to encode state in a more natural way. And that's what you see there. So this is composable in 1 degree. We can compose together these things, which I'm going to call iteratees, because they can consume a certain amount, and then they can produce a value when they are done. This value is called b. There's no explicit state. Now b is the final value produced by that. And in the case that it needs more, you pass it a function from the next input element to a new step. So basically this allows that fold function to start or call start initially with the first element in there, and to proceed step by step by step until your function returns done with the output value, at which point it stops and says, okay, I'm not going to feed this iteratee any more input. But there's one problem here, and that is, what if this, this start function, this iteratee, wants to consume input from a lot of different sources? Right now, we just have one fold function. And that fold function is promising to return a value of type b. So it's basically assuming that that iteratee will be done within the lifetime of the elements inside the list. In fact, that might not be true. We may have to pump this thing with lots and lots of data before that iteratee decides it's done and emits a value. So the next thing we do is make this composable at the level of folds by introducing some sort of input element that can basically represent an element of input or a signal that there is no more input, and the iteratee should emit whatever value that it has. And this allows us to take and we also modified the definition of fold left here. So instead of promising to return a b, it actually promises to return a step, which is the step advanced along as it can for the number of elements in that list. So what this enables us to do is take list A, list B, list C, list D, etc., essentially compose them all together in a single thing, and feed this iteratee to one after the other, after the other, after the other. And when we reach the definite end of that input, we can send it an end of file signal, which ends up internally causing that iteratee to say, okay, I'm never going to receive any more input. I better produce a value here. So there's one more thing. What does this look like when you've kind of renamed stuff? Well, it's pretty straightforward. You have your input element whose sole purpose is to wrap individual elements so you can provide an end of file signal to the iteratee that there's no more input and it should produce its output value. And then you have something like this, an iteratee, which has the more case saying, give me more input. Has another case saying done, which actually emits that final value. And then frequently you'll have either a control signal or something like this error handler saying, okay, something went wrong. Pass that information back up through the chain. So that basically this iteratee is allowed to produce errors. Other kinds of iteratees might be allowed to produce messages to request to seek to arbitrary points in a file or rewind or do other kinds of things. And then this thing that has until now been a list that we've been folding over now becomes an enumerator, which essentially folds over values of a given type of A. And you can call fold and produce it or feed it any iteratee and then get back an iteratee that is fully advanced as far as can be advanced given the amount of information contained in that enumerator. So the iteratee, it may or may not be done. If it's not done and you want a value, you have to feed it an end of file signal to produce one. But in many cases, you end up taking one enumerator and sandwiching it with another one to feed it lots of data across different sources. So you can actually, you could use option, but it's very handy in some cases to extend input with a third state called empty, because that allows you to do more interesting kinds of compositions. So I don't portray that in here, but oftentimes you will see an empty, another state in there that basically says there's no input here. And then an iteratee that gets no input, it just ignores it and says, give me more, or whatever it said before. But yeah, if you only had those states, I guess you could use option. So this is iteratees. That's all there is to iteratees, with one slight detail. And that is there's another abstraction called an enumeratee, which is a way to transform streams. You might imagine that just like in a list, you can take a list of A's and transform that to a list of B's, that there's some abstraction similar to that, because fundamentally an enumerator is very list-like, and in fact there is. It's called an enumeratee. And basically given an iteratee that consumes A's, it can produce an iteratee that consumes B's and internally transforms those into A's. So this is an example of kind of a stream transformer. It accepts elements of one input type and it transforms them to another. And together, these three abstractions, the iteratee, the enumerator, and the enumeratee, form essentially a complete algebra for iteratee-based I/O. You can do tons and tons of things. In real life, they don't look this simple. They look a lot more complicated. And that's because you have all kinds of crazy stuff here. You basically need to make iteratees a monad transformers. So all these things need to be transformers or have transformer versions. And you need that because, well, for various reasons, one of which is composition, another of which is functional purity, et cetera. Now let's take a look at how iteratees score on my report card. They're resource safe. They're really resource safe. It's basically impossible to leak any handles whatsoever. And the reason for that is the enumerator is capable of opening the resource, pumping the stuff out, and sending it to the iteratee until the iteratee is done or emits some error. When one of those things happens or it reaches the end of its resource, it can deallocate its resource safely. And all that's controlled by the enumerator. So actually with iteratees, it's impossible to leak resources. It's really, really, really safe. Composability, it gets a B+. So it's very, very composable. You can combine these things in all kinds of crazy different ways. It doesn't get an A, in my opinion, because some of the more complicated compositions are extremely complex and difficult to express with iteratees, but it is extraordinarily composable. There are many things you can think of, like, can we read from more than one input source at a time? Can we read from one input source and another, and the results of how fast we read from this one depend on what we read in this one? The answer is yes to all those questions. It's very complicated, but it can be done. High performance. This is specifically with respect to the JVM and the Scala programming language. Unfortunately, iteratees are not that performant. They are relatively slow because the first thing you want to do when you have them is compose them together. And every composition, every layer of composition adds additional overhead. We had to do some crazy things to use them ourselves internally, one of which is chunking. So instead of processing one element at a time, we process big fat chunks of elements. And that reduces the overhead of all this infrastructure on a per element basis to a level that it's manageable. They're reasonably type safe. They're not completely type safe. They do not get an A. There are some weird things about iteratees. One is the fact that you can feed an iteratee an end of file signal, and you have no guarantee that it's actually going to produce a value. You have no way of encoding that in the type system. There are also some other strange things when you have an iteratee that basically has a state that acts as a control signal to tell things to rewind or advance. It is really, really hard to develop a way of composing those things together in a generic manner that doesn't lead to nonsense in some cases. And as a result, they don't get an A for type safety, but largely they are type safe. So simple, unfortunately, they get a D because iteratees, even in the naive implementation, confuse many people. They're actually not that complicated. It's a little awkward to program with them, but usually you end up writing combinators that do things like take and drop while and other kinds of things to make them a lot more pleasant to deal with. But when you do the more advanced stuff with iteratees, they become very, very complex. And in Scala, the type signatures start growing to be multiple pages because you're doing type lambdas and just things go out of control like crazy. So they are not simple. They are not simple by any means. they can do incremental. In fact, they excel at incremental input and output. So let's take a look at an alternate way of phrasing things. We looked at one example where we kind of built up this functional I/O system starting from fold left. And it turns out we can do something very similar starting from map. Map's a lot simpler, and functional I/O built around this concept is much better at doing some kinds of things. So this is a basic map, but we have the same problem we had before at some point in our iteratee development, in that F has no memory. You send it an A, and it will always send you a B. It can't remember what's gone before. So the first thing we do is introduce kind of a mealy machine where you send it a value, and it returns the output as well as the continuation of itself, the next function in line to succeed it. And with that kind of encoding, you can have as much memory as you want. It's similar because now you can map values, but over time, I mean, it's more restrictive than a fold because you're forced to emit these Bs as you go along. So you're doing stream processing instead of folding to a single value.
It's a fold with a pure print line in each step.
Yeah, it's a scan. That's exactly what it is.
Because map makes you think that you can do things like parallel operations, which you can't do on the fold.
Yes, that's right. Yeah, it's bad terminology. I change it eventually. So what can you do with that? Well, you end up calling this thing that you can call map on it, you call it a stream. And the other one you call a stream processor. Or there are lots of different names for these things. In the Haskell world, there's a framework built around this that's called conduits. Stream processors by themselves aren't all that interesting because they can process values, they can transform them, they can manipulate them. If you extend this, like if B becomes an option of something else, for example, then you can conditionally emit values. You can do all kinds of interesting things. You can combine them together in various ways. But at the end of the day, you need a source for values, and you need some sort of sink. And for that, you usually end up with structures similar to this. You'll have a source, and you'll have a sink. And I'm missing some methods here. Typically, what you see in these kinds of libraries is source will have some sort of means of pulling data out of it in a semi-impure way. So it ends up being wrapped in some I/O monad, ultimately, that will return you a value as well as the continuation source to use for when you want more input. And sinks usually have a push method that ends up doing the same thing, pushing a value. But still, you can see some of the compositional properties here, even with the methods I've listed. Like you can take one of these stream processors, which form an arrow, and you can append it onto a source to produce a new source. Like if you can produce values and you can transform them, then you can produce values, basically. And the same way for a sink, you can take a sink and then prepend one of these stream transformers to it, and then call that thing a sink. It's just a sink of a different type. And there are lots of different ways you can combine the stream transformers themselves. Basically, anything that you can do with an arrow, you can do with these stream transformers. So you can do this one, and this one, and this one, transform from A to B to C to D, et cetera. And you can do other things as well. So the actual implementation for these look a lot more complicated because with all this impurity, you basically end up needing to introduce some notion of a transaction to help you not leak resources. And once you introduce that and the I/O monad, they end up being a lot more complicated than what you see here. So how do they do? Are they resource safe? Well, conditionally. Conditionally, these things are resource safe. You have to do some work. You have to wrap stuff in a transaction or a region to get resource safety, but you can make it work. They are very composable, so you can actually compose them more simply in some cases than you can with iteratees. When you have these two sinks and you can pull from one and pull from the other at different rates, it becomes a lot more natural to do some kinds of compositions. Pure, no. Unfortunately, the only thing that's pure, and it's not even pure in like the Haskell library conduits, is the stream transformer portion. That part can be 100% pure in most cases unless you need to do some sort of side effecting operation inside there. Everything else is contaminated with impurity. And it just, whether it's I/O or whatever, it just infects it and makes it harder to reason about. High performance, they're about on par with iteratees, at least if you do it by the element level. Every time you call the stream transformer to produce a new element, it's supplying a new function, and all that element by element overhead adds up. It's type safe. It's reasonably type safe. It's fairly simple. It's a lot simpler than iteratees. Most people find conduits, these stream processor libraries, a lot simpler to understand because they can think of it literally as in terms of a source of values, a pipe that can maybe change stuff over time in response to stuff it's learned in the past, and then a sink for values. And that's relatively simple. It's simple to think about. You can do incremental I/O with these things, and they're reasonably expressive. They're more expressive than iteratees for a given amount of work anyway. So I've given you kind of a taste for a few different ways of doing functional I/O. None of them are perfect. They all make different trade-offs. And I've been kind of looking for what's next. In my opinion, iteratees, they don't quite do it. Stream processors, they don't quite do it. Conduits, they're a little messy. I think definitely there's something out there that achieves more of the criteria I consider to be good. And what does it look like? Well, I think for one, it's going to have push-based sources to lend itself to asynchronous programming. The reality is that when you're programming out there in the wild, you can't pull a chunk of material instantaneously. There's always some sort of delay, and that delay you don't have control over, and it's proportional to the size of the data that you're trying to pull. And so in order to be efficient, push-based sources such as iteratees, where the enumerator is feeding all the values instead of the receptor pulling them, make a lot more sense. So it has to use chunking. In my opinion, Scala on the JVM. You cannot have a performant library that reads things element by element, unless your elements represent whole documents or something. You need to chunk it, and that makes the interface more awkward to deal with. And that's an inevitable reality, in my opinion, of doing high-performance functional I/O on the JVM. The chunking basically allows you to arbitrarily squash down the cost of all this extra stuff on a per-element basis. Something very interesting is possibly using monadic regions for resource safety. And that's part of the main motivations of iteratees is the fact that you don't leak resources. Well, if you use monadic regions to get that resource safety, then some of the benefits associated with iteratees go away, and you open yourself up to a more simpler model of programming that appears to be poll-based, but in fact it's not poll-based, and in which you're guaranteed that resources will be allocated at the right time by the regions that you're using. And I include some resources at the end of this if you want to dig deeper into that. And I think that there's going to be, if you hit some certain marks, I think there's going to be, if, for example, you hit performance marks, I think it's going to be perhaps a little awkward and a little complex to use. And I think that's just a necessary limitation of the JVM at this point, is that you can't have the cleanest, most beautiful, most composable code that runs performantly. And another option is, instead of doing that, I mean, there are certain points you have in designing any of these libraries at which you can insert something that's a little unsafe or something that's a little dynamic. And if you do that, it basically broadens the space that you can explore, and you can reach more of the other trade-offs. So if you're willing to sacrifice a little type safety or a little resource allocation safety, then you can get a lot of the other stuff on that report card. So here's some source code I recommend that you check out. Scala Z iteratees, which we've contributed to heavily. Yeah, it's not light reading, and there are type signatures there that will scare you. Haskell conduits, it's not a very clean library. It's actually very, very messy, but it does have all the basics in there. Scala conduits, which is an in-progress port of the Haskell conduits. That's not yet ready for prime time, but it'll be interesting to see how that shapes up. There's Scala Mealy machines if you want to experiment with that. And Haskell monadic regions. And Scala Z also has a region. I don't think it's fully complete yet. Yeah, it looks like it's a work in progress. But all these are really good resources. I recommend checking them out, reading the source code, playing around with them, and seeing what you think. So that's it. Any questions?